Hello, this is Dr. Lukes with another example for drawing. In this example, we will be looking at a problem that's taken from the McCabe-Smith textbook. And in this case, we are going to calculate the diameter and length of an adiabatic rotary dryer that's going to dry 2,800 pounds per hour of a heat-sensitive solid from an initial moisture content of 15% to a final moisture content of 0.5%, both on a dry basis. The solids have a specific heat of 0.52 BTUs per pound degree Fahrenheit, and they enter at 80 degrees Fahrenheit and must not be heated to a temperature above 125. Heating air is available at 260 Fahrenheit and a humidity of 0.01 pounds of water per pound of dry air. The maximum allowable mass velocity of the air is 700 pounds per square foot per hour. Okay, if we take that given information and rewrite it into symbols, I've got that information written in here. And the first thing we need to do is determine how we wish to operate. Well, that is not a rectangle. So if I bring the solids in here, do I want to bring in the air here? Or do I want to bring in the air here? Do I want to operate this concurrently or countercurrently? And in this particular case, because the material we know is heat sensitive, we want the air to come in with the with the material to be dried. So it will be co-current operation, okay? And that's because it's heat sensitive. Now, we were told that the dry bulb temperature is 260 Fahrenheit with a humidity of 0.01 pounds of water per pound of dry air. So we can use psychrometric charts, and we can find that the wet bulb temperature is 102 degree Fahrenheit. And we can use that to estimate the outlet gas temperature. Now, in this particular case, we don't have a lot of information, but when we read the book, they advise us that the number of transfer units will typically be, on the order of 1 to 2. So let's just assume it's going to be the midpoint of that average range, so 1.5. And the number of transfer units can be written as the natural log of the air coming in minus the wet bulb temperature of the air in over the air coming out minus the wet bulb temperature of the air out, but those will be the same. So the air coming in was 260, a natural log of this. Wet bulb temperature is 102, and that will be the same in each case. So if I set this equal to my expected value of 1.5, then we get that the temperature of the air coming out will be about 137 degrees Fahrenheit. Now this is based on an assumed value of 1.5, but that's a reasonable data. Now, we also are going to need some additional data. They gave us C sub P for our solid was 0.52 BTUs per pound degree Fahrenheit. And I have my liquid, which is just water. And then I'm going to have some water vapor. And you can look up values for these. Those are typical values. Now I also am going to need heat of vaporization, and the heat of vaporization is going to be at my wet bulb temperature, so 102 degrees Fahrenheit. If I look that one up in a steam table, the difference between the enthalpy of the vapor and the liquid is 1.037 BTUs per pound. Now, can we figure out how fast the water will vaporize? They told us that the mass of the solid is 2,800 pounds per hour of dry solid, and that it's going to come in with 15% per pound of, or 15 pounds of water per 100 pounds of dry solid, and it needs to leave with 0.005. And so therefore we need to vaporize 406 pounds of water per hour. Now, if we're going to vaporize this, I need to do it by heat. And so as this changes temperature, I'm going to go from liquid water to the boiling point. Then I'm going to vaporize, so I need that heat of vaporization. And then that portion that vaporizes will continue to heat to the exiting air temperature. The solid is just going to heat up to that exiting temperature, and the water that did not vaporize will heat up to that exiting temperature. So the components of my energy balance, or my heat duty, are going to be, so first the solid will heat up from 80 to 125 degrees Fahrenheit, and I can estimate that Q as the heat capacity for the solid times that delta T. Next, we're going to heat the water from 80 up to 102. Now, at that point, some of the water will vaporize, and then all of the water will continue to heat to their exit temperatures. Some of it will be in the liquid and go to the final liquid temperature, and some will be in the vapor and go to the final vapor temperature. So if we were to look at these contributions to the duty, then for the water, it's going to be heated from 80 to 102, and it's in a liquid form. Some of it's going to vaporize, and that's just BTUs per pound, not degree F. And then the material is going to continue to heat. The liquid is going to exit at 125 with a C sub P of 1.0. And the vapor has a C sub P of 0.45, and it's going to exit at a temperature of 137. Now we're not ready to add these up because we now need to multiply each of these times their flow rates. So the flow rate of my solid was 2,800 pounds per hour, and the amount of water that came in, so this initial amount, is 2,800 times 0.15. Now, a certain amount is going to vaporize. The amount we just calculated as 406 pounds per hour. The liquid that leaves is going to be 2,800 times 0.005, and the part that is in the vapor is, again, 406. So this is what's happening for my solid and my water. If I look this, actually do the math, the heat duty per pound of solid for the solid part. It's 179.3. And times 2800. 2800 is pounds per hour. Okay. Then I end up with a total for all of these is 502,040 BTUs per hour. So that's my heat duty for the solid and the water that came in with this. So now, what about the air? What's the energy balance component for the air? We can go to a psychrometric chart and find the C sub P for the moist air, and it is 0.245 BTUs per pound degree Fahrenheit. And again, this came from a psychrometric chart. And therefore, I can use this in an energy balance. Now, I can say that the Q is going to be the mass flow rate of that moist air times the C sub P times the delta T for that air. And the mass of the wet air coming in is going to be found from taking the dry gas times 1 plus H, the humidity, because we're having to work with these dry basis numbers. Now Q is given. I know C sub S because we found it from a psychrometric chart, and I know those temperatures. So therefore, if I put in these values, where these are degrees Fahrenheit, the C sub S is BTUs per pound degree Fahrenheit, and Q is in BTUs per hour, then I end up with that this is 16660 pounds per hour of the air. But H, we were told, is 0.1, so we get 16,495 pounds of dry air per hour. Now I can also figure out what the exiting humidity is from a material balance. So the exiting humidity, it started with 0.01 pounds of water per pound of dry air. But I am adding 406 pounds of water to the feed of 16,495 pounds of dry air. And so therefore the exiting humidity is going to be 0.0346 pounds of water per pound of dry air. So at this point we have figured out all of the basic mass and energy balance components. We've got temperatures, we've got flow rates. What we have left to do is to start analyzing the size of the dryer. All right, so we have found that the mass flow rate of the wet gas is 16,600 pounds per hour, and we were told that G needed to be less than or equal to 700 pounds per square foot per hour. So I can use this as a way of estimating what the area needs to be. So it's going to be mg over the superficial gas velocity. So 16,600 over 700 gives me an area of 23.8 square foot, or G, we could also say, is going to be the mass flow rate of the gas divided by the area. So now let's think about this, because we know we can't have G to be any larger than this. So do we want to choose a larger A or a smaller A? As we increase A, if we look at this formula here, we're going to decrease G, so we can choose any value of A larger than 23.8 square foot. And perhaps we'd want 24, but let's go ahead and figure out what the dryer diameter is, because if we can choose standard sizes, usually that's going to mean our equipment will be less expensive. So the area is pi over 4 d squared, and so therefore the diameter is the square root of 4 times 23.8 square feet over pi, and that comes out to be 5.5 feet. Again, we want to choose a diameter larger than 5.5 feet, so maybe we will choose D equals 6 feet, the next closest standard size. So now, how do we determine the dryer length? To do this, we need to find a formula from literature, or in this case our textbook, for this type of dryer. So for an adiabatic rotary dryer, we've got an equation. Our formula says that the length is equal to 8 times the heat duty Q over pi diameter G to the 0.67 and delta T, and this is the log mean temperature difference. Now, if D is equal to 6 foot, then this does change our value for G a little bit. So we have 16,600 pounds per hour over pi over 4, 6 foot squared, and so G is 587.1 pounds per square foot per hour. And now we have D, we have G, we were calculated Q earlier. We still need to get delta T log mean. Now delta T log mean is based on the air temperatures as compared to their wet bulb. So the air came in at 260 with a wet bulb of 102, and it left at 137 with a wet bulb of 102, divided by the natural log of these as a ratio. And if you calculate that, that's 81.6 degrees Fahrenheit is delta T. And so L is 8 times 502,040 BTUs divided by pi times 6 foot times G 587.1 to the 0.67 power, 81.6 degrees Fahrenheit, and L therefore is 36.5 feet when D is 6 foot. So we have now sized this dryer. Thank you very much for your time.